thank you very much, Bushi, and all the organizers for inviting me here. I'm gonna take you on a bit of a different route from previous talks, but in the afternoon I saw that Joseph will give a talk on the same topic, essentially. So I hope to do a bit of an introduction here. I'm from the University of Innsbruck, which, as you can see, is in a very different landscape from this one. Also different temperatures at this time of the year. All right. Now, I want to start by introducing the people who do most of the work, at least on this project. My group's much larger, but you wouldn't remember the names anyway. So there's Robert Kyle, who's a postdoc, Thomas Kauten, who's been on this project for quite a while as a PhD student, Sebastian Stier, who is now working on Waveguide interferometers that I hope to show you in the near the end of the talk. And very important also, there's two main collaborators, Czeslaw Bruckner in Vienna, who's working on theory related to generalized probabilistic theories, and Alexander Starmait at the University of Vienna, who's writing these fantastic waveguides. And this is supported by mostly the FWF, of which I'm also vice president, but unfortunately that doesn't buy me any grants, and the Canadian Institute for Advanced Research, which is curious, as I'm in Austria now for quite a while, but still they actually give me some money. All right, and I will start with this slide that will anger Ubushi a little bit because she's trying to disprove textbooks. And this is saying that when we use the word interference a lot, and these experiments make you think about what interference means. So in the standard setting, in this old discussion between Einstein and Bohr, we were looking at pictures like this, where particles or waves, not quite clear, could go through either of two slits and then would show an interference pattern as demonstrated, I guess, by Young originally. And in the quantum formalism, naively applied, we would write this wave function of a particle going through both of these slits as a superposition of two wave functions. And when we square that, absolute square that by Born's rule, we find that the probability that comes out is not just the sum of the probabilities of these particles going through the two slits, but there is an extra term, an interference term, and that really shows us the departure from a sort of classical statistical theory. Likewise, we can, or in reverse, we can define this interference term to be the difference between what we see with two slits open as opposed to what we would see with each individual slit. I'm going to say a lot why I don't like the slits in the end, but let me expand this to 3 slits. If we do the same calculation here, we find that there is the probability we get for 3 slits is really the sum of these single slits plus 3 pairwise interference terms, and now I guess it was Raphael Sorkin's idea to use this a generalized definition of interference, looking at this 3-path probability. If I rewrite it in this way, I have the 2-path terms minus the single path terms. And now if I say, well, could there be anything more that we haven't detected so far? We can define for something that is maybe not quantum physics or electrodynamics, some theory that goes beyond that. We could define a higher order interference term. In this case, it would be a 2nd order interference term or 3-path interference term that is defined as the difference between what we observe for 3 paths minus the right side of this equation here. And the equation, of course, holds for quantum mechanics and electrodynamics. And so we would expect such an experiment to show a 0 for this quantity IABC. All right, there is a bit of an overview of what I'm actually going to say. I'm going to say a bit more about this higher order interference, and then about how we went to measure this with as high as possible precision and accuracy. And I'll show you one of our main deterrents from that goal being the nonlinearity of any photo detector. And that's a, I wouldn't know, classical effect or experimental systematic error, but it's important for us to consider. And then I will show that this actually limits how accurately we can do these measurements right now, because it's very difficult to measure this nonlinearity as precisely as we can measure our signal. And then this is not the only thing we can do with these multipath interference tests. Another thing we can do is testing for hypercomplex representations of quantum mechanics as proposed by Perez. And this actually leads us to a desire to have better interferometers. Turns out that free space interferometers that I'm first presenting are not good enough for that. And so I'll talk a bit about waveguide interferometers in the end, to show you our sort of preliminary or first couple of results. All right, back to the second order interference. So the proposal was to measure this by performing 8 experiments where we would have 3 slits and then cover one of them in each experiment, 2 of them in all 3. And so we have a generalized quantity which also includes a background term which we call epsilon, and then at some point we had to figure out how to normalize it, and I think it was Raphael who suggested that we normalize this potential hypothetical higher order interference by the expected second order interference, as in a system that wouldn't show regular, first order interference. It would be quite uninteresting to look for higher order terms. In fact, they should actually be 0 if the first order interference is 0. Okay, and so this quantity became known as kappa, and Fukuchi's been talking about kappa for many years. All right. The big question is, of course, well, if we were to find anything interesting, unexpected here, we would probably be in trouble. There's a lot of stuff that will happen, and I don't really have time to go through all this, but this has created a lot of literature. For example, it's been shown that you could have a self-post-selecting quantum computer, which would then be even more powerful than a known quantum computer. There's other things that relate this absence of higher order interference to certain features or characteristics of quantum mechanics. For example, theories that fulfill a tomographic principle, meaning that we can assess the state by measuring all first order interference terms, is logically equivalent with something that has no higher order interference. Seems very simple if I say it this way, but I think it's actually quite profound. I'll say a little more about the density cube on the next slide. There's also something I don't understand yet, which is quartic quantum theory. Maybe one of you knows more about this. And then there's also connections between other things, for example, the Tyrrellson bound or a contextuality bound with the absence of higher order interference. And I find that's also a very interesting connection. Clearly, this has something to do with the structure of Hilbert space as well, and the measures. All right. I said I wanted to say something more about density cubes, and that is because very often these types of experiments with the higher order interference fall under the category of testing Born's rule. But it's not only testing Born's rule. And it's really Czeslaw Bruckner and Borivoje Dakic's merit to have come up with a toy theory, in a way, a theory that actually uses Born's rule as an axiom, but still could exhibit higher order interference. And that is by proposing that instead of using a density matrix, we use a 3-dimensional object, a density cube, for representing the state. Clearly, at this point, we wouldn't know how to measure this or what that has to do with nature. But you should be allowed to think about it. And so this density cube has 8 matrix elements for a qubit. For a Q-trit, of course, it would have 3 by 3 by 3, 27. It's actually quite big. It would have sort of off-space diagonal elements, which would show up as second-order interference terms, even though the measurement rule they impose is still a trace rule, Born's rule. In that sense, the testing for higher-order interference could be testing for any number of deviations from quantum theory, not just a violation of Born's rule. All right. And then I said I wanted to say something about slits. And for those of you who've been here last week, you heard all about this. So it's only for those who haven't been here. Slits have been plaguing me for a long time. There was some desire to do this initially with slits, just because maybe the ancient discussions about interference were all done in terms of slits. Most experimentalists know, though, that to actually measure something with interference, you never use slits. You usually use interferometers of some kind. Calibrating optics you do with interferometers, because they're just easier to handle. Slits are small and they're difficult to block and unblock. And as you see here in this picture, this was actually a manufacturing error in our 2010 experiment, which limited the accuracy of finding the absence of higher order interference. Okay, and then also it turns out, of course, that this assumption that I could just add the wave function, the naively calculated wave function for one slit and the one for another slit is wrong, especially if these slits are close together. I think the first one to actually see this, but formulate in a bit of a funny way, was Hans de Reed in the Netherlands, who calculated by finite difference time domain the propagation of these waves through the slits, and could show that having an open or closed slit next to another one makes a difference for the field. And the way I usually phrase this actually is to say that the superposition principle from a mathematical point of view applies to solutions of a differential equation or a boundary value problem, but you cannot change the boundary conditions, right? Because you will get solutions. If you change the boundary conditions, you will get new solutions that do not respect the other boundary conditions. So you can't just go ahead and add these and believe that this would be that these would be really orthogonal or respect the boundary conditions. And in this way, this naive application of superposition principle to slits will lead to an apparent higher order interference, non-zero kappa value, even though nothing's wrong with Born's rule or electrodynamics. All right. Of course, these effects will disappear exponentially if you make the separation between the slits larger. But I propose that instead of doing that, we should really go with interferometers. I will just skip over this. There were also experiments in one experiment in another system with NMR, and this is basically a similar version, just done with a different optical system. So what I'm saying is that we should really go with this, the mass send interferometer. Why? Well, it has kind of orthogonal modes here and there. Of course, in real life, these paths will have a finite separation, but if I have a Gaussian beam going through here, and I separate this by several beam diameters, then the naive probability of a photon somehow going from here to here can be exponentially small. And in that sense, I can again use, in this case, proper superposition principle. I could actually put a wall up here between these two branches, and I would really have separated solutions left and right in the or upper and lower arm completely. Another thing is I can actually control the phase very precisely, and I can sort of go to a particular point in phase space without having to having to rely on position in the far field. And finally, I will lose almost no photons if I get good components in here. For slits, everything that hits the slit barrier will be lost. Whereas in here, I can get almost 100% out if I look at both the output ports. All right. Of course, for 3 paths, I would have to expand this in a way. And now here, if I choose the reflectivities right, I can make this a completely symmetric, almost completely symmetric interferometer. There's, of course, 2 more inputs that I'm not showing. This is basically a 3-port device or 6-port device, which has 2 non-trivial phases. And on the other hand, here it's a little tricky. You know, every splitting is done in 1 to 2. And at the time when we thought about this, I really wanted something that split it 1 into 3 at a point. And so instead of doing this kind of setup, we went for a different type of beam splitter, a hologram, and you can buy these off the shelf. You put them in the beam, and they make 5 laser beams for you. Just like you can buy another hologram that makes a line so that you could maybe level something when constructing or when hanging pictures. You know, you can get a line hologram. So here we have a mass end interferometer again with a holographic beam splitter that produces 5 beams, 5 Gaussian beams. And these Gaussian beams go through shutters whose apertures are much larger than the beam itself. So if now someone tells me, well, what are your non-classical paths, or what are these sort of diffraction effects? And if I calculate the total power diffracted by the open beam aperture, and assume that all this goes into the wrong direction, it's 10 to the minus 22. Okay? If I ever get to that level of precision in the experiment, I'll retire. That will not happen, so I can't retire. Okay. So we have shutters here, and then we can control the phases, and we recombine this at a similar beam splitter. And in fact, we can only measure one output mode that's a completely symmetric superposition. The other output modes are a bit more complicated. All right. This is then how the entire experiment looks. It's a bit more complicated by the fact that we have different types of light sources available for doing this experiment. For one, we can just use a red laser, which would come in here. In another case, oh, sorry, there. In another case, we could use a so-called heralded single photon source, where we take a blue photon, produce a pair of red photons, split one off, detect it, and send the other one into the interferometer. And then as a detector, we could also use either a photon counting detector or a photodiode that gives us a continuously varying output signal with the applied light power. All right, and I'll give you this. This is not really very useful, this picture. I want to draw your attention more to this thing. This is the actual shutter array. So this is a macroscopic thing. There's a hole for every beam. I think right now they're closed here. And they're really like valves, like water valves. So beams go through or not, and when they go through, they don't lose any, not any noticeable power. All right, so we started out with these measurements, and then we found this. So this would be our kappa, and this is called kappa 3 now. I should say, why do we have a 5-path interferometer? It's because off the shelf, this thing made 5 beams, all right? And then we also discovered that a 5-path interferometer contains 5 choose 3-path interferometers, and that's 10. So there's 10 different 3-path sub-interferometers, and that's an advantage, because if there's any systematic problem, you know, any phase drift or so, it's much easier to find out if you have something to compare to than if it's only a 3-path. Okay, so we can measure kappa 3, we can also measure kappa 4 and a kappa 5 with them. So we measure this, and now if you look carefully, there's a 0 here, and the black line, which is the mean of this distribution, is far away from 0, actually. I'm not showing the error of the black line here, or the error of the mean, but it's much smaller than this deviation. So it's significantly non-zero. Where does this come from? This shows that we also have we very careful about the correlations in the errors of the various different subinterferometers. So let's look at these numbers here a little bit. This is the raw data, and so I call this the classical regime. If I take a laser beam and I measure it with a continuous photodiode, I call it semi-classical if I take the laser beam and count the photons that come out, and I call it quantum if I take this single photon source. But these are really just, whether you consider them quantum or classical really doesn't matter. So we look at these numbers and we see that for almost all of them, except for this bottom row here, the error bar, which is the standard error of the mean, is much, much smaller than the actual value. And in fact, this one here is positive, that one's negative, that one's also negative. Is that significant? And kappa 4 and kappa 5, I don't really have to look at. Where does this come from? Well, I already told you before, detector nonlinearity is really an issue. And any detector, any measuring device will have a limited range or a limited amount of linearity. Even your best voltmeter will eventually have its specification limited by its linearity, meaning that whatever input signal you apply, you get a response, and if it's not a line, but some kind of curve, it's nonlinear. In fact, in this experiment, we don't care what the slope of the line is. You know, what we get out doesn't matter if it's milliwatts or some other unit, doesn't matter, but it should be linear. Why? Because if we think of this as a Born's rule test, and we measure psi square as a flux or as a probability or a power, then any nonlinearity would be sort of multiplied or convoluted in, I guess, to Born's rule, and we'll get different exponents. And so there's some basic nonlinearities that are known. For a photon counter, there's always some kind of dead time, meaning that the detector is blind after it has detected a photon, and that basically acts as nonlinearity, because as the photon rate increases, it will miss more and more photons. For photodiodes with amplifiers, it turns out the nonlinearity sits in the feedback resistor of the amplifier, which is interesting maybe for experimentalists. And then it turns out that also your voltmeters will have nonlinearity. All right, so how do we measure this? The problem is, it's easy if you have a source that is super linear and that tells you now I'm outputting this much power, but you would be measuring the combined nonlinearity, which doesn't help you. So what we do is a reference-free measurement. We take two lasers, put both beams on the detector, and then we put one, the other, and both off. And if you do that and vary the power level of these two lasers, eventually you get a huge cloud of points, which is the where you show the measured total signal over the residual signal, which is the measured total minus the measured single ones. And then you can try to fit a model nonlinearity function through this cloud of points. And you see that it's already quite small. This is for a photodiode. Here's the actual signal in volts, and this is the residual in millivolts. So we're at 10 to the minus 3 level here, 10 to the minus 4 level in parts, in some other cases. In fact, in this case, we would say that the nonlinearity is 25 parts per million, meaning that the output deviates from a straight line by 25 ppm at the worst point in the curve. And it turns out for our evaluation of the data, we have to be really, really careful and precise about what we mean. So we actually have to try out various models, because it's not, for an arbitrary device, it's not a priori clear what shape this thing should have. And by adding more and more fit parameters, you can make it look really funky, but that's really useless too. So in that sense, we have to do an error analysis on this model and make sure that we've chosen the right number of degrees of freedom, say in a polynomial fit. And then once we do that, we can go back and plug it into the expected output by quantum mechanics from our interferometer, and then look at what we see as a deviation from this expected output under the action of the nonlinearity. The the next problem is that in order to get a proper expectation, we also need to understand the interferometer very well. So turns out we first have to sort of calibrate or understand the interferometer, and there's and we do this by the rules of quantum mechanics. Now you could say, isn't that a kind of circular reasoning? You know, we use quantum mechanics or electrodynamics to say what we expect to see, and then we want to look for a deviation. And in this case, it's really just to see how does the nonlinearity act on the data that we would expect to see from quantum mechanics, not trying to show an actual higher order interference deviation. So we do quantum state tomography for this interferometer, which in fact, by the tomographic principle, includes all the binary terms, no higher order terms, so it only looks at two path sub-interferometers. We get some kind of density matrix, and then we generate all these data that we would expect to see if quantum mechanics hold it and held, sorry, and we would measure all the possible terms from single path to 5 path in our Sorkin measurement. And then we take this reconstructed data and we add or multiply in the nonlinearity model, and then we generate theory, and then we can compare that theory output or that simulation to what we see in the experiment. And this is sort of the final result. So there's quite a few points. These are always the kappa 3, the regular, and then the 4 path and the 5 path kappas. And here is the case for the heralded single photons, or quantum regime, if you will. And this is for just applying sort of stronger laser light. And you see that for the heralded single photons, already the data themselves are consistent with the 0 kappa in all cases. But we also see that the theory and the experiment deviate maybe a little bit, but not significantly. The difference is much more pronounced, or the influence of the nonlinearity is more pronounced here in this case with the laser data. So here we have various data points. The orange and the red one are the theory, so this is the expectation under the action of nonlinearity. And you can clearly see that for a single photon counter, which would be the points below here, the nonlinearity of the photon counter predicts that we will see a negative kappa. And this is because it's basically a saturation effect, whereas the other nonlinearity you saw is curving up. So it overestimates the higher order terms, and therefore gives us positive kappas. Okay? And if we do this now, we also see that the experimental data are always, or reasonably nicely within the error bars of our simulation. You can also see that in this case, the experimental data are actually have much less scatter. In fact, the error bars are too small to show here than the prediction we get from the nonlinearity. And that is the difficulty in establishing exactly what the nonlinearity parameters are for a given detector. In that sense, at this point, it wouldn't make sense to improve the experimental statistics anymore unless we knew the nonlinearity better for our detector. All right, and here this is the same thing where we sort of show the deviation between the simulation and the experiment for these 3 different experiments. And now all of them are sort of consistent within one error bar with a 0 kappa, so with the absence of any higher order interference. In that sense, you could say we've now shown that there is no higher order interference in our interferometer to the level that we show here, which is the size of the error bars, and this is about 10 to the minus 5 for sort of measuring with a photodiode, about 10 to the minus 4 measuring with a photon counter, and it's a bit more closer to 10 to the minus 3 if we actually use single photons. And that is just because we don't have enough single photons. We don't run for long enough. So in that case, we could really improve by running longer or making some other improvements that reduce the measurement. All right. So that was all about higher order interference. In fact, these results, we posted that on the archive already almost a year ago, and have been going rounds with referees, and it would be very entertaining to look at these reports, but I don't do that. All right. So as a side thing initially, there was the idea that we could also test for a hypercomplex representation of quantum mechanics. Now, quantum mechanics we usually represent by complex numbers so that we can track the phase. But there is not much that prevents us from, instead of using complex numbers, using hypercomplex numbers. And so the first reasonable set of hypercomplex numbers are the quaternions, invented by Hamilton. Quaternion number has sort of 4 components, a real component and 3 imaginary components. And these 3 imaginary units fulfill a cyclic anti-commutation relation. And we're actually very popular for writing electrodynamics. They're still popular in computer graphics, actually, for representing operations in affine spaces. And had been suggested for quantum mechanics too. Now there's you probably all know Stephen Adler. He wrote an entire book about quaternion quantum mechanics, which is about this thick, about 700, 800 pages, but now does not believe in quaternion quantum mechanics anymore. He says he's actually proven that it's useless, or that we won't see any effects in the far field. Turns out, though, he had to retract a bit on that claim recently, so we're still interested in really doing these experiments. And our idea of a test goes back to Asher Perez, who proposed that we could again take a 3-path interferometer, or 3 scatterers, as he phrased it, and look at the phase differences between the scattered waves of all these three paths. Okay, so we would have three scatterers A, B, and C, and calculate the phase angle for every one for every pair. And now, if this is complex quantum mechanics, then these phases have to lie in a plane. So the phase angles have to sum to 2 pi. If you're in a higher dimensional space, they could actually lie on the cone, so to say, and in that case, the angles would actually might be, some of the angles might be smaller than 2 pi. And he put this into a criterion, into a parameter that he called f, which is a term that contains all these phase cosines. And if as I said, if psi is complex, then these angles would be coplanar, and so f would have to be 1. If psi is quaternion represented, then the angles could be non-coplanar, and there could be an f smaller than 1. Doesn't mean that it actually occurs in nature. And you could ask yourself whether, what are these phases? They might have to be of a different nature. In fact, he suggested that one use, maybe in a neutron experiment, use different types of materials where one would sort of create a force based on sort of a phase based on the strong force, strong interaction, whereas another one maybe would be more based on a weak interaction. Or I really have no idea. Okay, so naively we thought, well, we can do this with an interferometer. But then it turns out we look at our interferometer and measure these. We get 10 different sub-interferometers with 3 paths. We measure this and we find f's much smaller than 1. Yes. This is quite different. This the Sorkin parameter is just a sum and difference of count rates, whereas this here actually retrieves the angles of only the 2-path terms. So it never actually measures the 3-path term. And in fact, it couldn't detect the higher order interference. Of course, it also assumes a superposition principle. In fact, if f was found to be larger than 1, you would say the superposition principle must be violated here. So we measured this naively, and we got I wasn't going to publish that, and I didn't. So, because there was whenever so as experimentalists, we usually educated to be skeptical about our results for good reason. Because if you're not skeptical, you would say, great, I found quaternions in nature. But in most cases, as we all know, it's some mistake in the experiment. In fact, it's the same with Bell's inequality. It's very easy to build an experiment that does not violate Bell's inequality, right? And if you don't try hard, you won't achieve it. In that sense, if you work with the bias that Bell's inequality was never violated, you would never violate it. So same here. So we have to work harder, and it turns out any kind of incoherence, any averaging over these numbers here, any phase drift will basically ruin this sum of cosine terms and will make f smaller than 1. So this criterion, as already pointed out by Perez himself, only works for pure states, or sort of, in my words, a perfect interferometer with perfect contrast. And that's of course not easy to get, especially in a free space interferometer. I should also mention that other experiments have been published, or at least posted recently, which in fact do what has been done in the neutron experiment a long time ago, which measure a different property. Quaternions are non-commutative, and so you could imagine that if you applied two different quaternion phases in different order, once like this and once swapped, if there was a difference, that would also be a hint that there might be quaternions. And this has been done recently by Philip Balta's group, and they measure this difference in the phases for the one and the other order, and they find it to be smaller than 0.03 degrees, whatever that means. We have no reference at this point. All right, and so now for us, this free space interferometer doesn't work. So we went to go for waveguide interferometers, because in a free space interferometer you overlap two beams, and somehow if you're a good experimentalist, you can make the overlap good and really good, but it's never going to be perfect. So we really want an interferometer that couples two single modes, because then there can't really be any incoherent part anymore. And so we want to do this by using waveguide couplers. So here is two waveguides that have a certain coupling between them, C. And if we launch light into one of these waveguides, it will oscillate back and forth between these two waveguides because of the coupling. And if you cut the structure after a certain length, a certain fraction of this coupling length, you will get the 50-50 beam splitter, or actually any ratio that you would like. The same works for three modes, here drawn side by side. One can make a 1-to-3 splitter with equal power ratios. And in fact, what we're using right now is a splitter that is where all the waveguides are sort of symmetrically coupled. Turns out, though, now we have some polarization problems, and this may not have been the ideal choice. These waveguides that we use are actually laser-written glass waveguides. Many of you will have heard about this. One takes a femtosecond laser and basically modifies the refractive index of the glass locally, and this will stay. And now you take your glass chip and you basically draw it along under the laser and turn the laser off and on. And by creating this sort of a series of dots, you create a continuous waveguide, and you can make sort of arbitrary, almost arbitrary 3-dimensional structures. They have very low numerical aperture because the refractive index difference between the written core and the surrounding is very small, but they also very, very low loss, and the couplers can be done with very high precision. So this is really, really a nice system. And this is done by Alexander Samite's group, who just moved from University of Vienna to University of Rostock within this talk even, if you noticed. In fact, he's actually moving right now. All right, and so we have a waveguide interferometer with this splitter. We launch laser through a fiber array into this waveguide array, and in this first realization, Now, of course, we have a waveguide, but we also need to block the paths. And that's not easy, because obviously they're in a solid. And so our first approach was that we would build the equivalent of a Michelson interferometer, where now we have these three paths terminating at a polished surface of the chip. And then we would approach these surfaces with little mirrors so that light goes back into the chip, depending on whether the mirror is actually on the waveguide chip, like here, or away from the waveguide chip, so that whatever comes out spreads and doesn't return, or at least not much. And that'll be done in a minute or so. And this works, or did work, but it has one problem that might be obvious to some experimentalists. In fact, in real life, it's really hard to butt this up against the chip exactly at the point of the waveguide. And in fact, we had to use some index matching gel in here to avoid an extra cavity, and all of that had the effect that the phase of the reflection really depended on how much pressure we applied. So it was really tricky to actually get the same phase setting at every point. And phase averaging is exactly what we not want, as I pointed out before. So unfortunately, for the quaternion measurement, this approach was completely useless. We did measure the Sorkin parameter kappa, but also that was not great. You see, this is a hugely broad distribution, which comes out to have a almost zero mean, but the precision is actually worse than in our previous approach. And that is why currently we're working on this one, or we actually have it already. This is a Mach-Sender interferometer now on the chip, which has little holes in it. And funny enough, if you make this hole into the waveguide and do nothing else, light almost jumps across. This hole is a few 10 microns wide, and the waveguide NA is so small, in fact 60 microns here, so small that light almost propagates straight and doesn't suffer much loss. But what we can do now is we can insert a wire into this hole and actually block the light relatively well to at least a 100-to-1 contrast here. These holes, if you're interested, I can skip over this, how they are made. It's not so important, and just show you the final setup. So Sebastian Stier, the master student, figured out how to thread 3 wires into holes and move them up and down to either cover or not cover the waveguide. And now the advantage is that this is absolutely phase stable. So we thermostat it, and we don't see any drifts over a day. It's fantastic. On the other hand, if we wanted to manipulate the phase, that might become a little tricky. We'd have to apply heaters. And also with these wires, we can block and unblock without changing the phase at all. And yet, as it is always with first experiments, we find a non-zero kappa. So I can't give you super good news, but at least the interferometer itself seems to be performing very well, and we'll see how this goes then for Perez test, and maybe also improve the Sorkin type. All right, and this leads me to my conclusions. I would say interferometers are preferable because they avoid non-classical paths and sort of errors in applying a naive superposition principle. We have so far the highest accuracy Sorkin measurement, or the tightest bound, I would say, and now we have some really interesting waveguide interferometers that could be used for a number of fundamental tests. And if you have any more questions, please let me know. Thank you. Everyone's hungry, huh? I think at this level, no, because we, I would say the accuracy is not so high that you could really gain something from it. There's one advantage, I would say, and that is if you had a theory that predicted a certain functional form. For assuming you have a theory that says Born's rule is psi to the 2.5, with only the kappa from a 3-path interferometer, you could not say what the exponent is. unless, well, maybe you could fit it in with different phase space points or so. I'm not sure. But if you had the higher order terms, then you could clearly expand this into a power series and get a bound on every coefficient in the power series, for which you have a measurement. Kappa 4, 5, 6 sort of would directly go with the coefficient in a sort of relaxed Born rule. Well, the shutters are kind of black, but it might scatter back somewhere, and then the question is, could it scatter forward again through the other, through another opening or so? And in fact, we've been thinking about putting sort of, we could put walls between the beams, right? Black walls that would make sure that any backscatter would really.
Yeah, I would be worried that it backscatters onto your holographic beam splitter and then comes off of that into.
And then it would have to scatter forward again. Right?
Yes.
Because that's anti-reflection coated, so it would actually.
Yeah.
That would,
you have numbers on these reflection coefficients.
We might have numbers. I think we actually I don't have a number in my head, but I think a student of mine calculated once or tried to measure how much would come back by sort of artificially blocking the other beams, although it's tricky, right? Because once you block them, then you've also blocked the path. So it's not so easy to measure.
When we did this for this parametric amplifier interferometer, it turns out it works to do the calculation, say if the anti-reflection coating is 10⁻³ efficient,
right?
What interference do you get?
No, and it might also help to in this case, we could make the shutter when it's closed could be, and it was actually black. Unfortunately, this coating that was applied to the brass kind of got rubbed off a little bit, so now they are sometimes a bit shiny. Yeah, that's right. That's a good point too.
Because if you have backscattering, then that can change the source. And that can also effectively lead to a non-zero kappa without you knowing it.
Yes, but then we're talking about, I think in fact this is something that could be happening in the waveguide interferometer.
Sure, that's what
there we,
yeah, that's the one that I'm...
Single mode back. In fact, that's one of the things we're investigating right now. But in this free space thing, at least in the heralded single photon source, there's no way this would really change the source, but it would have to up-convert back into the blue laser. So
no, I'm talking about the third one, actually, the waveguide ones, where you have this really...
In the waveguide one, I think that's actually the case. In fact, it's quite tricky to stabilize the laser while it's coupled to the whole thing, right? Because it's not so easy.
If no further questions, we'll thank both the speakers again.